All right, guys. We didn't have enough time to study for Unit 6, so I'm recording this video, and I'm holding the camera with one hand, so it might be a little shaky. Unit 6 is thermochemistry, so you have to remember about endothermic and exothermic reactions. So the two types of reactions, endo is taking in energy going in. Exo is energy coming out or releasing energy. So think of it like entering and exiting, okay? So when we draw the graphs for endothermic reactions, we start at a lower energy for reactants, and we end at a higher energy level at the product. And we just draw a little curve connecting it. So the distance between the reactant to the product, this is how much energy the graph have changed or the reaction have changed. So that's our delta H. And in this case, we're going up. So it's an endothermic with a positive change in energy. All right, and then from the beginning, let me use a different color. From the beginning here to the very top, okay? This distance from reactant to the top, this is from here all the way to the top, okay? That is your activation energy, or EACT. That's how much energy is required to get the reaction started. And on the very top, this point, this is the tipping point, okay? So before this point, the energy is still climbing up. And after this point, the energy starts to go down. So this is our transition state. So just remember these five. We got reactants, products, activation energy, transition state, and our change of energy, delta H. All right, and for exothermic reaction, it's the total opposite. So instead of starting at a lower energy, this time we start at a higher energy, and we end at a lower energy, and we just connect between the two. So in this case, our reactant is still in the beginning, our product is still at the end, but our change of energy is still in between reactant with product. So this distance right here, that's how much energy this reaction have changed. It went from up here all the way down there. So this is a negative delta H. And our activation energy is much lower. So again, you see how this one goes from reactant to the very top. Same thing for this one. We start from the reactant, goes to the very top. So this is a very short activation energy. So this is our activation energy. And on the very top, again, that's our transition state. We'll just put TS, okay? So this is an exograph. After this part, the graphing part, we kind of talked about specific heat. So our equation is Q is equal to M times C times delta T. And where Q is equal to heat or energy, and the unit for Q is either joules, kilojoules, calories, or kilocalories. Kcal and uppercase cal is the same thing. And then for M, that's our mass. Mass is between kilograms and grams. Specific heat is C. This one, it depends on what the other units are, okay? So the unit will vary. And then our delta T, that's our Remember delta, that's change. And then T is temperature, change in temperature. So that's our overall equation for this. Remember this triangle, okay? Q is always on the top, and then everything down is below. So we got, if you're solving for Q, the equation is going to be M times C times delta T. That's our first equation. Solving for Q, you just block Q. So Q is equal to M times C times delta T. If you're solving for M, you just block M, and we have Q over C and delta T. So M is equal to Q over C delta T. And if you're solving for C, you just block C. That will be Q over M delta T. So C is equal to Q over M delta T. And the last one, if you're solving for delta T, cover that, is equal to Q over MC. So delta T is equal to Q over MC. The reason why we do this triangle is to make it a lot faster to figure out what we have to do. Otherwise, you will just have to do the math way. So for example, this is our original formula. Q is equal to M times C times delta T. If I want to solve for delta T, I will have to divide M and C on both sides of the equation, and then M cancels out with M, C cancels out with C. So our delta T is equal to Q over MC, which is the same as that. So as long as you remember this triangle, you will be able to find all of the formulas, okay? And heat, Q, that's just our energy. M, that's simple, that's just our mass, how heavy something is, that's how much energy something has, and that's how much temperature have changed. So what exactly is specific heat? So everything in our world have their own specific heat. So for example, the specific heat of water or versus copper, Cu. So I think copper is 0.385. Let me double check. Yep, 0.385 joules per grams per degree Celsius, and water is 4.184 joules per grams degree Celsius. So what this means is if you have a 1 gram of water and another 1 gram of copper, okay, to increase this temperature, this block of water, to increase the temperature by 1 degree Celsius, we will need 4.184 joules of energy. For this piece of copper, to increase the temperature by 1 degrees, you will need 0.385 joules of energy. So copper requires much less energy to heat up compared to water. So if I give both of those, let's say 100 joules of energy, how much temperature will the water change? So you just do 100 divided by 4.184 equals, put that in the calculator, that will equal to approximately 23.9 degrees Celsius. And if I do the same to this piece of copper, 100 joules of energy, that will, how much energy will this one increase? So 100 joules divided by 0.385 joules is equal to 200 and 59.7 degrees. So you can see the difference. So for this piece of water cube, if I increase the energy by 100 joules, it will only go up by 23 degrees. If I increase this piece of copper by 100 joules, it will go up by 259 degrees. So that's a huge temperature change. Okay, so that's what specific heat is. Specific heat is how much energy a substance or material needs to absorb before their temperature can change. So the less specific heat, the easier to heat up. The more higher the specific heat, the harder it is to heat up. Okay, and the last thing to remember is, for example, right here. So let's solve two example problems. So the first example problem is how much heat must be absorbed by 20 grams of water to increase its temperature from 283 degrees Celsius to 303 degrees Celsius. So question is asking for question mark heat. So heat, which variable is heat? That would be Q. How much of heat must be absorbed by 20 grams? So every time you see grams, that would be our mass. So this is our mass. And then the temperature, we have T final and T initial. So this is our initial temperature, 283. So that's our TIAL. That's our T initial. And 303, this is our T final. So our delta T, the formula, is equal to T final minus T initial. Okay, so let's solve this. Oh, we still need our C. So a common specific heat to remember is water. The water specific heat is always 4.184 joules per grams degrees Celsius. Okay, so again, we're solving for Q. So our formula needs to be Q is equal to M times C times delta T. And our M is equal to 20 grams. So we put 20 grams times our specific heat is that one. So 4.184 joules divided by grams degrees Celsius times our delta T is equal to final 303 minus initial 283. Delta T is equal to, put it in my calculator, 20 degrees Celsius. That's how much temperature there is changed. So 20 degrees Celsius. So grams cancels out with grams. Degrees Celsius cancels out with degrees Celsius. So we have 20 times 4.184 times 20 joules. So equals 20 times 20 times 4.184 equals 1,673.6 joules. So that's how much energy must be absorbed by 20 grams of water to increase their temperature from 283 to 303. Okay. All right, next part. Another example. So a 4-gram cube of gold was heated from 274 K to 314 K. How much energy was used? Oh, K, by the way. Our change in temperature right here. The unit for temperature is either degrees Celsius or Kelvin. So K stands for Kelvin. That's a unit for temperature. So again, normally if we just have a single number and we will have to convert it between Kelvin and degrees Celsius, but since they're both change in temperature or delta T, we don't really care about what is the unit difference between those two. We just care about how much they have changed. So our T final is 314. This is our T final, TF. And our T initial is this one, TI. So 314 minus 274 is equal to 314 minus 274 equals 40 Kelvin, or it's the equivalent of delta. So delta T is temperature change. So we can interchange the unit. Okay. You can only do this for delta T, not TF, TI, or TF. So be careful about the unit. And then our 4 grams, this is our mass, M. How much energy was used? Oh, okay. So we are solving for Q again. So Q is equal to M times C times delta T. Our mass is 4 grams, 4G, times specific heat of gold is that one. So 0.129 joules divided by grams degrees Celsius times 40 degrees Celsius. Okay, so cancel out, grams and grams. So we have 4 times 0.129 times 40 equals 40 times 2 times 0.129 equals 20.64 joules. So this is how much energy must be used to increase the temperature of a 4-gram piece of gold from 274 Kelvin to 314 Kelvin. All right. Let me see if I can find another question for solving different variables. Nope. Well, it's the same thing. You just plug all of the variables into the formulas and you solve for each one. Okay, so this is what's going to be on tomorrow's test. It's pretty easy and pretty recent. Just remember the graph, the two endo and exo graphs. What is endothermic? What is exothermic? The formula for this one, how to find the other formulas, and the different units, how to convert between each unit. Okay, so let me do one more example for unit conversion. So for example, you have, let's do grams and kilograms. If you have 5,000 grams, that is equal to 5 kilograms, because every 1,000 grams is equal to 1 kilogram. So the K stands for 1,000. Okay, so 1 kilo is 1,000. So this works for heat as well. So if you have 60 kilojoules, how many joules is that? So that's 60K, so 60,000. So just put 60,000. That's how many joules there is. Okay, same thing goes for calories. So if we convert 1,000, let's say, 1,000 small calories is equal to 1 kilocalories, or 1 uppercase C calories. That's the same thing as kilocalories. So if you have 5.5 kilocalories, that how many small calories is that? That would be 5,500 small calories. If you can't do it in your head, you will have to do the unit conversion setup. So for example, if you have 600 joules is converted to question mark amount of kilocalories. So first of all, we need to know the conversion between joules to calories, small calories, right? So every 1 calorie is equal to 4.184 joules. So to set this up, we will start with what we know and end with what we don't know. So we start with 600 joules times, we can go from joules to small calories. So we put small calories times, and then we can go from small calories to big calories. So big calories. That's 2 different calories, okay? That's a lowercase and that's an uppercase. So whatever unit you have on the top, you will have exactly the same unit down below. So if you have J on the top, I'll put J on the bottom. If I have small cal on the top, I'll put small cal on the bottom. So I know every 1 calorie is 4.184 joules, and I know every 1 kilocalories is 1,000 small calories. So now we just have to cross out anything that's dividing by itself. Joules cancels out with joules, calories cancels out with calories. So we have 600 divided by 4.184 divided by 1,000. So if you put this in your calculator, you would get 600 divided by 4.184 divided by 1,000. Equals 0.14 uppercase kilocalories. Okay, so that's our unit conversions. So if you understand all of this, you should be fine. Good luck on the exam, and this is our last one. It's 400 points, so do study it.